Let me say a little bit about the homework problems in section 1.1. I had said earlier that starting in section 1.3 we're going to do some qualitative analysis of differential equations that we can't solve. Actually, we're doing it already in problems 4 and 5 in section 1. Here's a population model where p is the unknown function we're trying to find, t is the variable. Notice that the right-hand side does not involve t, only the unknown function p. That means you can't just do an antiderivative if it were a function of t only. You could, but it's a function of p only on the right-hand side. Generally, it'd be a function of p and t, but this is called autonomous if it's a function of the unknown function only, p in this case. And actually, this is a separable problem. Autonomous problems are always separable, so we'll learn how to solve it in the next problem in theory, but only in theory because it's actually very difficult in practice, almost impossible. So essentially, we can't solve this analytically, but we can say some things qualitatively about it, and namely you can tell when, for what values of population is this increasing, what values is it decreasing, and all you have to do is see what values of p. The right-hand side is positive, then it's increasing, it's negative, it's decreasing. Same thing here, except that you have to factor this. This one's already factored for you. Now, problem 7 is an application, a radioactive decay application. This is very similar to the bank balance problem number 2 that we did in the last section, except that in the bank balance problem, the rate of change of your bank balance is proportional to the current bank balance. Here, the rate of radioactive decay is proportional to the amount you have left, but it's a negative constant. So it's similar to the bank balance problem, but with a negative constant. I'm going to look at an old test problem that's similar to a couple of your homework problems, section 1.1. This is if I of t, the unknown function, is the amount of an isotope that's present, iodine in this case. It satisfies I prime equals minus alpha I. It's, in other words, the rate of decay, the rate of decrease is proportional to the amount you have left. And the alpha is a function of that isotope, but it isn't given in this problem. What is given is the half-life. That means the amount of time that it takes the isotope to decay to half of what it was originally. Every 20 days, the amount of isotope goes down by a factor of 2. That's what half-life of 20 days mean. The question is, what is alpha? Well, you solve this even though you don't know alpha, and it's just like the savings balance problem. The solution is just going to be any constant times e to the minus alpha t, and then you say, well, when t is 20, that's going to be half of the original amount, and you solve for alpha in that way. So some of the problems, they give you the alpha and ask you what the half-life is. Others, they give you the half-life and ask you what the alpha is. In both cases, the differential equation is the same, and the solution, you're looking for a function I of t whose derivative is just minus alpha times the I itself. Well, as we said, a solution to that is just e to the minus alpha t, because you take the derivative of e to the minus alpha t, and what do you get? You get e to the minus alpha t, which is I, times minus alpha. And any multiple of that is also a solution. So the general solution would be I of t equals c e to the minus alpha t, where c is the original amount present at time equals 0. Okay, let's go into section 2. This is separable problems. This is actually the section where we learn more about actually solving differential equations than probably any other section in the book. This is the most important one as far as actually solving them. And we said all of chapter 1 is about the single first-order equation, y prime equals f of t and y. That's a general first-order differential equation. Y is the unknown function, t is the variable that it's a function of. And usually we can't solve that. If this is a function of t only, we just have to do an antiderivative. but if it's a function of t and y in general, it's simply impossible to solve. However, if that right-hand side, which is generally a arbitrary function of t and y, happens to be a function of t times a function of y, this is called a separable problem, and that we can solve. For example, if dy dt equals y times t, then that's separable and we'll be able to solve that. On the other hand, if dy dt is y plus t, that's not separable and we won't be able to solve it. Well, actually we will later in section 1.8, but it's not separable, so we can't solve it in this section. Okay, so let's suppose the problem is separable, so the right-hand side is a function of t times a function of y. And by the way, if it's a function of t only, that's separable because h is just 1. If it's a function of y only, that is an autonomous problem, then that's also separable. G is just 1. But in general, let's say we have a function of t times a function of y. Otherwise, we're out of luck in this section. How do you solve that? Well, you should always write the derivative, instead of writing it as y prime, write it as dy dt, and think of that dy dt as being dy divided by dt. And essentially it is, because the definition of dy is dy dt times dt, so we're not really pulling a fast one on you here. Just think of this derivative as dy divided by dt, and you separate it by getting all the t's and dt's on one side and the y's and dy's on the other. So essentially you just divide by that h of y, the function of y, and multiply by dt, so you get your g of t dt on one side and your 1 over h of y times dy on the other side. And now it's a question of doing two antiderivatives. See, because what does the dy mean? That means y is the variable. What does the dt mean? That means t is the variable. So you've got g of t, where t is the variable to integrate. Here you've got 1 over h of y, where y is the variable to integrate. If we couldn't separate it, if this were a function of t and y, you can't just take an antiderivative because you don't know what y is, or if there were t over here, you couldn't do it. So you've got to get all the y's on one side and the dy's and the t's and dt's on the other, and then it's a question of doing two antiderivatives here. Well, that may be difficult, as you know, even if the right-hand side is only a function of t. That can be impossible, often is impossible to do the antiderivative, but well, let's assume you can do the antiderivative of both sides. For example, suppose we had dy dt equals t over y squared. That is separable because that's 1 over y squared times t. And you take the dt on this side and the y squared on that side. And now you've got it separated. That is, all the y's and the dy on one side, the t on the dt on the other. Now you just take the antiderivative of both sides. The antiderivative of y squared is 1/3 y cubed. Antiderivative of t is 1/2 t squared plus arbitrary constant. Now you could say there's an arbitrary constant on both sides, but there's no point in writing them both out because you could just take the arbitrary constant here on the left-hand side and you still just got one arbitrary constant. So normally you just put the plus c on one side and not both. And now, if the problem was separable, t over y squared, we separated it. We integrated it successfully. Now we have to solve for y, and it's possible in this case. However, there are a couple of things that can go wrong. Well, three things. It might not be separable. If this were t plus y squared, then it's not even separable. But assuming it's separable, it may be impossible to do one or the other of the integrations. Assuming you can do both integrations like we could here, it might be impossible to solve for y. For example, this one is separable. There's no t on the right-hand side, but you can just say that the function of t is 1. So you separate everything, no problem. You can do the integrations, but now you can't solve for y. So what do? Well, you can just leave it like that. You can actually solve for c from the initial condition, and you basically got the solution implicitly, but you just can't solve for y. If that's the best you can do, that's the best you can do. So if you have a separable problem, you can separate the y's and the t's, and you've got two antiderivatives to take. Well, as you know from Calculus 2, antiderivatives are not always easy, and they're often impossible. There's whole huge books full of formulas for antiderivatives. You don't need to learn all those. There's a sheet at the bottom of the class web page that has a list of the antiderivative formulas that you need to know, and any formulas that aren't on this list, I'll either give them to you or you won't be expected to know them. So basically the only ones you really need to know are the antiderivative of x to the n is x to the n plus 1 over n plus 1, always plus constant. That works even when n is negative and even when n is fractional. So for example, square root of x, that's x to the 1/2. That would be x to the 1/2 plus 1, x to the 3/2 over 3/2. So 2/3 x to the 3/2. So this works for any n except n equals minus 1, and that has a special formula log of x. So these are just a review from Calculus 2, but maybe been a while. So basically you can take the antiderivative of x to any power whatever, fractional, negative, including minus 1, using this special formula. Antiderivative to e to the x is e to the x. Antiderivative of e to the ax is 1 over a e to the ax. Just take the derivative of the right-hand side and you'll see that it gives you that. Derivative of sine is minus cosine. The antiderivative of sine is minus cosine. Why? Because the derivative of minus cosine is sine. The only thing hard here is to remember which one has the minus. So the derivative of sine is cosine, therefore the antiderivative of cosine is sine. You just need to memorize those. So these are basically, there's really just 5 formulas here because this is a special case. You need to know the antiderivative of x to any power, including minus 1. You need to know the, antiderivative of e to the x, antiderivative of sine and cosine. But if you understand the chain rule, you can take antiderivatives a lot more complicated formulas. A lot of the antiderivatives and the problems in the book, you have to use the chain rule version. What do I mean by that? Well, the derivative of u, so if the derivative of x to the n plus 1 over n plus 1 is just x to the n. Why? Because take the derivative, you get n plus 1 times x to the n plus 1's cancel. That's what the 1 over n plus 1 sitting there waiting to cancel the n plus 1. You get x to the n. Well, what if you don't have x to the n plus 1? What if you have 3x plus 5 to the n plus 1? Or cosine of x to the n plus 1? What if this isn't just x? What if it's some more general function of x? Well, then the derivative of u to the n plus 1 by the chain rule is n plus 1, and that cancels with this n plus 1, times u to the n times u prime. In other words, it's this. So for the chain rule says the derivative of this thing here by the chain rule is this. The n plus 1's cancel, you get u to the n, and then you get a u prime. Well, the antiderivatives, you're just working backwards on your basic derivative formulas. So if you have u to the n times u prime, we know the antiderivative of that. So basically, if you have u to the n, if instead of just x to the n, you have, sine of x to the n or e to the x plus 3x plus 4 to the n, you better hope you have the derivative of whatever I said was inside the parentheses there. If you do, you're in business. If you don't, you're out of business. You just have to get lucky, basically. It's surprising how often you get lucky in homework problems. But so if you have a 3x square plus 1 to the n, you better have a 6x here. Or if you don't have the 6x, if you just have a x, that's good enough because you can bring a 6 past the integral sign, but you can't bring the x. So if you have a, 3x squared plus 1 to the 10th power, the antiderivative, you better have a 6x here. In that case, the derivative is 1 over 11 times 3x squared plus 1 to the 11th power, if I said that right. And this is just the chain rule version of the case n equals minus 1. And this is the chain rule version of e to the x. So if you have e to the something other than just x, or t, whatever the variable is, I'm assuming the variable is x. If you have e to the x squared, for example, then you better have a 2x there, or at least an x. You can get the 2, but you can't get the x if you don't have it. because x can't cross the integral sign, but the 2 can. So if you have e to the x squared, you better have a 2x there, in which case the antiderivative is just e to the x squared. It's just the chain rule backwards. Derivative of e to the x squared is e to the x squared times 2x. So if you have e to the x squared here, you better have a 2x there. You better get lucky. And if you don't, if you just have a, like if you have just e to the x squared and you just have a 1 here, you're simply out of luck. There's no way to take the antiderivative. You need the 2x there. And then these are the chain rule versions of sine and cosine. If you have sine of x squared, you better have a 2x there. Cosine of x cubed, you better have a 3x squared there, or at least the x squared, because the 3 you can multiply and divide by 3 and get it. So if you have cosine of x cubed times 3x squared, the antiderivative is sine of x cubed. Why? Because derivative sine of x cubed is cosine of x cubed times the 3x squared. Just chain rule in reverse. So you'll learn to do these with practice, but basically there's these 5 formulas you need to just memorize. They're the important ones, and then you need to know how to apply the chain rule backwards. So most of the problems in section 2 are simply solve this differential equation, separable differential equation. For example, dy dt equals ty quantity squared. Well, that's t squared y squared, so that's separable because function of t squared times function of y squared. You separate it, divide by y squared, multiply by dt, and then you have t squared dt on this side and 1 over y squared dy on the other side. You do the two antiderivatives. You're going to have one arbitrary constant. Well, technically 2 of them, but any old number plus any old number is just any old number, so there's really one arbitrary constant. Might as well just add it on the right hand side only, and you get the general solution. And down in the other exercises, you have to they give you initial conditions, so you have to plug in, for example, once you solve this and get the general solution, there'll be an arbitrary constant in the solution. You plug in t equals 0, x equals -2, and see what the constant has to be to make that work. So these are the same, except there's an initial condition. You have to find the arbitrary constant. All of these problems, there'll be one arbitrary constant after you solve them. So they're all separable. For example, this, you just multiply by e to the y and dt, so you'll have e to the y dy times dt. That's pretty easy to do both integrations, both antiderivatives. There's no t on the right-hand side. That's an autonomous problem. Their autonomous problems are always separable because you can consider that the function of t is just 1. This one looks like it's not separable at first glance, but if you factor out a 1 over y, you'll have a t over t squared plus 1 times 1 over y, and it is separable, so sometimes it's not obvious. You have to do a little bit of work to separate. So separate, get all the y's and dy's on one side, the t and dt on the other side. If you can't, then it's not separable. Do both antiderivatives. You shouldn't have to know any antiderivative formulas other than the ones I just showed you that are at the bottom of the class web page, so print that and use it. And in these problems, you have to go ahead and find the constant which makes the initial condition work. Here's a typical test problem. This problem is separable. The t times 1 over 5y to the 4th, etc. So you separate it and get all the y's on one side and the t dt on the other side. Antiderivative of t dt is 1/2 t squared plus arbitrary constant. This you have an antiderivative of 5y to the 4th plus 9y squared minus 6y times dy. That antiderivative is y to the 5th plus 3y cubed minus 3y squared. So after you're able to do both antiderivatives, but you can't possibly solve this for y, so the instructions say if you can't, you can't. Just leave it like that. You can find the constant from the initial condition. So you plug in t equals 1, y equals 1, and that c has to be 1/2 to make this work when t is 1, y is 1. So sometimes it's not separable and you're dead. Sometimes it's separable but you can't do the antiderivatives. Sometimes you can do the antiderivatives but you can't solve for y. But sometimes you can, like this problem. And at least one of your homework problems is similar to this test problem. So let's look at it. It's a Newton's law of cooling problem. That means that the Newton's law of cooling says the rate of change of temperature, say you have a cup of coffee, the rate of change of the temperature of coffee is proportional to the difference between the temperature of the coffee and the room temperature. In this case, the room temperature is 70. So rate of capital T stands for the unknown temperature. T is the variable, so you're trying to find big T of little t. And you know the differential equation is the rate of change of temperature is minus some constant times T minus the room temperature. That is a separable problem because it's autonomous. However, you're not given K. You're given initial condition that when time is 0, temperature is 130 degrees. So you can solve this. It's separable. However, they didn't give you the K. So it looks like they've given you two initial conditions. They tell you that when time is equal to 0, the temperature is 130 degrees. That's the normal initial condition. But they also tell you that the rate of cooling at T equals 0 is 10 degrees per minute. In other words, they give you two initial conditions, even though it's a first order equation. They give you two initial conditions. They give you T of 0 is 130 and T prime of 0 is minus 10. Well, the reason they give you two initial conditions is they didn't give you the K. So basically you can consider that the second initial condition is just to help you to find K. You basically just say, well, when the temperature is 130, T0 is 70, dTd little t is minus 10, you can use that to solve for K. Turns out to be, looks like 1/6. Then you solve. So one of the initial conditions is basically just because they didn't give you K. Once you know K, then you really just have one initial condition, first order equation. It's separable. You solve it and plug in the initial condition and there's the solution. And finally, there's another homework problem in section 2 that involves it's what's called a mixing problem. That and there's an example, but let me take a problem from an old test here. It's a little simpler than the problem they give you in the book. And it says you have a 200-gallon tank full to the brim with pure water, 5 gallons per minute of a brine solution, that means a saltwater solution, with 0.1 kilograms per gallon salt flows into it. Since the tank is full, 5 gallons per minute of well-mixed solution overflows onto the ground. So you got 5 gallons of this brine solution coming in, and since it's already full, 5 gallons per minute is spilling out onto the ground. The differential equation is we're trying to find S of T, which is the amount of salt, not salt water, but the actual amount of salt. So S of T, the function you're trying to find, is the number of kilograms of salt in the tank, and the problem only asks you to find the differential equation with the initial condition. Don't solve it. So how do you get a differential equation? Well, the rate of change of salt in the tank is what? Well, coming in, you've got 5 gallons per minute of 0.1 kilograms per gallon. That means 5 times 0.1, or 0.5 kilograms per minute is coming in of the actual salt. Okay, 5 gallons coming in, 0.1 kilograms per gallon. That's 5 times 0.1 kilograms per minute coming in. So that's positive. On the other hand, you've got salt going out onto the ground because the mixed solution is spilling out onto the ground. So how fast is it decreasing? Well, there's 5 gallons per minute of that also. Which means 5 gallons times the concentration. Well, what is the concentration? So coming in is 5 gallons per minute with 0.1 concentration, so 0.5 coming in. Going out, there's 5 gallons, but what's the concentration of what's going out? Well, it's whatever S is divided by the total. I'm sorry, the amount of salt going out is the number of gallons per minute of mixed solution, which is 5, times the concentration. But what's the concentration? Well, it's not 0.1. That's the concentration of what's coming in. Concentration of what's going out is however much salt there is divided by 200 gallons, because if S is the total amount of salt in the tank, there's 200 gallons, then the concentration is S over 200, whatever S is. So S over 200 times 5, that's where the S over 40 comes from. The 5 over 200 is 1 over 40. So you're coming in, you've got 5 gallons times 0.1. Going out, you got 5 gallons times S over 200. So that's the total rate of change of salt in the tank. And the initial condition is that when time is 0, there's no salt. It says it's pure water. So there's your differential equation initial condition. It is separable because it's autonomous. There's no t on the right-hand side, so you can solve it. Didn't ask you to in this homework problem, though. Just write the differential equation and the initial condition. So those two old test applications will help you solve these two problems. This is a mixing problem. Basically, you have to solve the differential equation and get the amount of salt as a function of time. Once you have that, you can answer any of these questions here. This problem is the only difference between this and the coffee problem is it's hot chocolate instead of hot coffee, basically. And again, don't even worry about what they're asking until you solve the differential equation. Once you have the temperature as a function of time, or the amount of salt as a function of time, you can answer any question they ask you. They might ask you, how much, what's the temperature at a certain time, or they might say, when does the temperature cool to such and such? That's what they ask here, but either way, once you have the solution, you can answer the questions.